Hi everyone, our lesson today is two color objects probability with ordered sampling of 2 and without replacement. We have the following problem to solve. An urn contains 12 blue objects and 8 red objects. Without looking, we withdraw according to the following rules. So we have here 3 rules. The first one, we withdraw 2 objects, and the second, we register the result of the withdrawals in order, and the third, after each withdrawal we do not return the object to the urn. So the question is, what does the sample space consist of? We are withdrawing 2 objects, so the sample space must consist of 2 symbols. Let's have a look. We have here all the objects, 12 blue and 8 red. So this is the group of red object, and this is the group of a blue object. The first one is 8 and the second one is 12. So going back to the question, we have the group of blue from 1 to 12 and the group of red from 1 to 8. We can combine them into one group, and now we are withdrawing object, let's say B8 and R5. Or we can withdraw R1 and B4, but we cannot withdraw B4 and B4 because we are not returning the object to the urn. So we can say here that the sample space consists of sequences composed of 2 symbols with different letters, such as B9, R5, R3, R7. Or we can say that the sample space consists of sample point of size 2. So sample point of size 2 means sequence that has 2 symbols, and therefore R is equal to 2. Now the question is, what is the number of elements in the sample space? So before we know the number of elements in the sample space, we have to know the number of objects we are dealing with. We need to know the total number of objects. We have 12 blue objects and 8 red. The sum is 20 objects. So let's have a look. This is the urn, and all these objects can be mapped into objects numbered from 1 to 20. So if we write these objects together in one group, we can map them into numbers from 1 to 20. And now we are withdrawing from all these numbered 20 objects here. So going back to the question, we have the group of all objects and we map them into numbers from 1 to 20 as we see here. And so now we are taking 2 objects in order without return from this group here. And that is permutation. Why permutation? Because order is important. And this is permutation without replacement because we are not returning the object to the urn. So we have 20 objects, and we are generating a sequence of 2 objects out of the 20 objects we have under the 2 conditions, which are order and no replacement. In such case, we use the permutation formula without replacement of 20 objects taken 2 at a time. So permutation of 20 taken 2 at a time equal to 20 factorial divided by 20 minus 2 factorial. Or we can do it quickly. We start the product from 20 and we multiply in descending order for 2 numbers only. So 20 times 19 equal to 380 objects. So the sample space consists of 380 sequences. Each sequence has the size of 2. We can find the total number of possible outcomes by using the table of withdrawal event. So we write this event in order: first withdrawal and second withdrawal. The first withdrawal can happen in 20 way, and the second withdrawal can happen in 19 way. So why we are reducing the number of objects here? Because we are withdrawing without return. So in the beginning we have 20 objects available, and after the first withdrawal we have only 19 objects available for withdrawal. Now we use the multiplication principle. 20 times 19 equal to 380, and that is the number of sequences in the sample space. So before we continue, we are going to define disjoint sets. If we have sets A and B, we say that these sets are disjoint if they have no common element, such as set A and B. There is no any common element between them, therefore their intersection is a null set. And we have to remember the axiom of disjoint event. If two events are disjoint, then they have no mutual element, and the probability of first event or the second event is equal to the probability of the first plus the probability of the second. And same things can be generalized for more than two events here. So now we are going to define elementary events. And why do we define elementary events? Because we are going to create complex events out of them later. So we are going to consider these elementary events: BR, which is withdrawing blue object first and red second; RB, withdrawing red first and blue second; BB, which is withdrawing blue and blue; and RR, withdrawing red first and red second. Now, how do we get all these elementary events together? The answer is we use the tree diagram. So we define B as withdrawing the blue object and R as withdrawing the red object. And in the first withdrawal we may get either blue or red, and in the second one we may get again either blue or red. So we may get blue blue, blue red, red blue, and red red. So these are all the possible outcome of these two events, and these possible outcomes are the elementary events we have. So going back to the same problem, considering the elementary events, these events are all disjoint from each other, and their union is going to be equal to the sample space itself. We are going to prove that later on. So these four events are called, or subgroups are called, partition in the sample space itself. It's as if sample space is a house and we created partition, we created room. Every room is one of these subgroups here, one of these subgroups, and their union is going to be the house itself or the sample space itself. Now the question is, how many blue and red objects can be withdrawn one after the other? So the blue can be withdrawn in 12 ways and the red can be withdrawn in 8 ways. So using the multiplication principle, we can just multiply them together and get 96 ways of withdrawing blue and red. We can also use the table of events, and we write here the first event withdrawing a blue object and second event withdrawing red object. So the first event can happen in 12 ways, and withdrawing red object can happen in 8 ways. We multiply them together and we get 96. So 96 ways of withdrawing blue, red. Now, what is the probability of withdrawing blue and red objects one after the other? So we divide the number of outcome of the event blue, red over the number of possible outcome which is 380, and we get 0.25. So 0.25 probability means what? Means if we repeat this experiment around 100 times, we are going to get approximately 25 withdrawal of blue and red. And now the question is, how many red and blue objects can be withdrawn one after the other? So before we studied how many blue and red object can be withdrawn, and now we are asking the opposite, how many red and blue can be withdrawn. So this is exactly the opposite. We have just to multiply in opposite way, so we can withdraw red object in 8 ways and blue object in 12 ways, so we have total of 96 ways. Or we can use this table of events to get the same result exactly. So we have 96 ways of withdrawing red and blue objects. So now the question is, what is the probability of withdrawing red and blue object one after the other? We divide 96, the number of possible outcome for red and blue, over 380, which is the total number of all possible outcome, or the number of elements in the sample space, and we get again 24 over 95. So 24 over 95 means that if we repeat this experiment 95 times, we are going to get approximately 24 withdrawal of red and blue. Or if we read it other way in decimal, the probability is 0.25, which means if we repeat this experiment 100 times, we are expected to get 25 withdrawal of red and blue. So the question here, how many blue and blue object can be withdrawn one after the other? If we have 12 blue, so if we withdraw for the first time, we have a 12 way of withdrawing, and if we want to withdraw for the second time, we have 11 blue object remaining, so we are going to get only 11 way of withdrawing the second blue object. And in such case, we can use the multiplication principle by multiplying 12 times 11. Now we can say that we have the blue objects are numbered from 1 to 12. The number of all objects, number of all blue objects is 12, and we are generating sequence of 2 objects out of the 12 objects we have under the following 2 conditions, which is order and no replacement is allowed. In such case, we can apply the permutation formula without replacement of 12 objects taken 2 at a time, and that is going to be equal to 12 factorial divided by 12 minus 2 factorial, or we can just multiply 12 times 11 and we get 132 ways of withdrawing blue and blue object. We can also use the event table, and we write the first event withdrawing the first blue object, and the second event withdrawing the second blue object. The first event can happen in 12 way, and the second event can happen in 11 way. So their product is 132. We can use either this formula or we can use the table of events. Now, what is the probability of withdrawing blue and blue object one after the other? We divide the 132, which is the number of possible outcome of this event blue, divided by the number of elements in the sample space, which is 380, and we get 0.34. So if we repeat this experiment around 100 times, we are expected to get 34 blue and blue withdrawal out of the 100 itself. Now the question is how many red and red objects can be withdrawn one after the other. So we have the set of red objects from 1 to 8, and we are withdrawing 2 of these objects one after the other. So we are permuting 8 objects, taking 2 at a time. Why? Because order is important. So we can use a permutation formula, and since we are not replacing the object after we withdraw it, then we are going to use permutation formula without replacement. And this is going to be equal to 56. So we have 56 possible outcome of withdrawing red and red together, one after the other. Or we can use the event table. So here first event is withdrawing red ball, and second event is withdrawing the second red ball. So for the first event, we have the number of ways that this event can happen is 8, and for the second event, the number of ways this event can happen is 7. We multiply them together and we get 56. So now what is the probability of withdrawing red and red objects one after the other? So we divide 56 over 380 and we get 0.14. So for every 100 experiment of withdrawal, we are going to get approximately 14 red and red withdrawal. And now, after we computed all the possible outcome of the elementary events, we want to really prove that their union is going to be equal to the sample space itself. How do we prove that? If we add the number of possible outcomes for each elementary event together, and we get the number of elements in the sample space, that would mean that the union of these 4 elementary subgroups is going to constitute what? The sample space itself. So let's see. We write the event and we write its corresponding possible outcome. So for withdrawing blue-red, we have 96 possible outcome. For red-blue, we have 96. And for blue-blue, we have 132 outcome, and for red-red we have 56. Now let's add all of them together and we are going to get 380, which is the number of elements in the sample space itself. So that would mean the union of all these events is going to give us the sample space itself. So 380 is called the number of all possible outcome, or the number of sample space element, or the number of sample space point, or the total number of the generated sequences, and all means the same. And now we are going to create complex event based on these 4 elementary events. So let's start with the first one. What is the probability of withdrawing 2 objects of the same color? So we can withdraw either blue-blue or red-red, and their probability is the sum of probability of blue-blue and red-red. So we just substitute and we get 0.47. Now the other question is, for complex event, what is the probability of withdrawing 2 different color balls? So we have 2 different colors we are going to withdraw. So that is, we either withdraw blue-red or red and blue. So we add their probability together and we get 0.5. What is the probability of withdrawing blue-blue or blue-red? So these events are 2 disjoint events. So we add their probability and we get 0.6. So now another complex event. What is the probability of withdrawing red-red or red-blue? So these 2 events are disjoint, and we add their probabilities together and we get 0.4. Another complex event, what is the probability of withdrawing at least one blue object? So we can withdraw blue, red, or the opposite, red, blue, or blue, blue. So we are now forming a complex event out of these three events. So probability of blue, red, or red, blue, or blue, blue is equal to the probability of each event, and that is, we add them together, is equal to 0.8. Again, what is the probability of withdrawing at least one red object? So we can either withdraw red, blue, or blue, red, or red, red. So each of these events contain at least one red object. So these events are disjoint. So the probability of their union is equal to the probability of each event individually, and we add them together and we get 0.65. And now we have the last and biggest complex event, which is withdrawing blue, blue, red, red, blue, red, or red, blue. Actually, the union of all these events is going to be equal to the sample space. Therefore, here we have a certain event and its probability is going to be just 1. So the union of all these events is going to be equal to the sample space itself. So now we have a certain event, or we can add all these probabilities together and we are going to get 1. That is for the certain event. Thank you for watching and have a good day.